Today we shall prove that Rn is a metric space with Euclidean metric, and then we shall prove that Rn is a metric space with a metric other than Euclidean metric. So first of all, what is Rn? Rn is um, a set, and this is also called n space. Rn is also called n space. It consists of a set of n tuples of real numbers like x1, x2 to xn, where each xi belongs to set of real numbers for I from 1 to n. So this is n space. So we shall prove that the map D from Rn cross Rn to R by, this is the map which is defined by d of x y is equal to summation I from 1 to n xi minus yi whole square whole power 1 by 2. We shall prove that this map D is a metric. It satisfies the four properties of metric. So we shall verify the four properties of metric, and here x and y are elements of Rn. They are the n tuples of real numbers x1, x2, xn, and we have y1, y2 up to yn. So x and y are such elements. Now we shall verify the four properties of metric. First of all, the property of non-negativity, whether D is non-negative or not. So it is clear that because D involves the summation of xi minus yi whole square I from 1 to n, since there is a square which is involved in the definition of D in this function, it involves whole square, and the sum of all the squares is also non-negative here. And then if we take the power 1 by 2 of this summation, we shall also get the value which is non-negative real number. So it is clear, or you can say that it can be seen that it can be shown that it is clear that, so it is clear that D of xy is non-negative. Non-negative means if a real number t is non-negative, so t must be greater than or equal to 0. Number 2, we shall prove that D of xy is 0 if and only if x is equal to y. So if D of xy is 0, then this summation I from 1 to n xi minus yi whole square whole power of this summation 1 by 2, that's equal to 0. Then it is possible if this value, the summation of xi minus yi whole square equals 0, then it is possible if for each I xi minus yi whole square equals 0, then we can easily conclude that xi equals yi for all I. When for all I xi equals yi, then we can say that hence the n tuple x equals the n tuple y. Similarly, in the same way, I mean in the opposite way, we can prove that if x equals y, then the value of d at xy equals 0. Number 3, the property of symmetry, d of xy, which is equal to I from 1 to n xi yi whole square whole power 1 by 2. It can be written as summation I from 1 to n yi minus xi whole square, that's equal to d of yx. So symmetry holds here, the property of symmetry holds here. Now the most important property which can be you can say the which is the most important part of this example. So we must focus on this triangle inequality, and if z is equal to z1 z2 up to zn, then for all x y z belongs to r power n, what we show here, we shall show that dxy less than or equal to dxz plus dxy. This is the triangle inequality. And what is xy? Xy are taken in the beginning here, so no need to mention again and again. Xy are these elements. I have just taken z, so then for all x y z belongs to Rn, we must show that and this inequality holds, which is called the triangle inequality. And now we prove this one. D of x y equals to summation I from 1 to n xi minus yi whole square whole power 1 by 2, and we can add and subtract zi. that is I from 1 to n xi minus zi plus zi minus yi whole square whole power 1 by 2. Now we put ai equals xi minus z and bi equals zi minus y. And it is just for making our derivation simple, and that's why we put ai equals xi minus z and bi equals zi minus yi. Then what we have, then what is dxy? Dxy equals I from 1 to n ai plus bi whole square whole power 1 by 2. Now consider the Cauchy-Schwarz inequality. For the real numbers ai, bi belongs to R, so we shall write the Cauchy-Schwarz inequality for ai, bi belongs to R, and here what we have, and here I from 1 to n. So what is the Cauchy-Schwarz inequality? The Cauchy-Schwarz inequality is mod of summation I from 1 to n ai bi less than or equal to summation I from 1 to n ai square whole power 1 by 2 into summation I from 1 to n bi square whole power 1 by 2, and this is greater than or equal to what? The number without modulus, summation I from 1 to n ai bi. This is the Cauchy-Schwarz inequality, and this number is greater than or equal to this number, of course, because there is a mod here. So if we have, for example, minus 2, so the mod of minus 2 is 2, which is greater, and if we have plus 2, the mod of plus 2 is again 2, so they are equal. So we have the inequality in this way, less than or equal to the mod of this number might be greater or equal than this number. So this implies that summation I from 1 to ai bi less than or equal to summation I from 1 to n ai square whole power 1 by 2 summation I from 1 to n b I square whole power 1 by 2. Now we multiply by 2 on both sides. We can do it. Then what we do? We can add and subtract this number. If I write here separately, I just added this term on both sides. Okay, so the summation can become out. In this way we have ai square plus bi square plus 2 ai bi less than or equal to, and what is this? What is this? This is, we apply here the formula is our x square plus y square plus 2xy. What is x? X is root of, what is x? X is root of summation I from 1 to n ai square, and y is a root of summation I from 1 to n bi square. And I think so it is not so difficult to understand here, because you just apply the formula where x is equal to under root summation I ai square, and y is equal to summation I bi square. So this is, here is x square, here is y square, here is 2xy. So that's equal to x plus y whole square, which is summation I from 1 to n ai square plus summation I from 1 to n bi square. This is our x. So x plus y whole square. Yes. And this is equal to summation I from 1 to n, ai minus bi whole square less than or equal to summation I from 1 to n, ai square plus root of summation I from 1 to n, bi square whole square. When we take a root on both sides, so what we have this value, this one, okay. And what is ai and bi? Ai is xi minus zi and bi is zi minus yi. So put the values again, once again. Ai is xi minus zi, and what is bi? Bi is zi minus y, so that's equal to zi plus yi whole square 1 by 2 less than or equal to summation I from 1 to n. What is ai? Xi minus zi whole square plus root of summation I from 1 to n, zi minus yi whole square. So we have ultimately summation I from 1 to n, xi minus xi here, here is the positive sign, yes, here is negative sign, so my apologies here, because here is a positive sign, so bi is zi minus yi, and then what we have, zi are cancelled, so we have xi minus yi whole square whole power 1 by 2 less than or equal to I from 1 to n, xi minus zi whole square plus I from 1 to n zi minus yi whole square. So what is this? This is dxy. If you see here, this one, this is the value of dxy. So by definition of d, we can write in this way: dxy less than or equal to dxz plus dzy, which is our triangle inequality. So D is a metric. D is a metric on Rn. And here you must remember that here D is a Euclidean metric. Okay, this definition is the definition of Euclidean metric, and for for the n space, okay, for Rn. So we have proved that Rn is a metric space with the Euclidean metric. So what does it mean? Because D is a metric, of course, therefore the pair R and D, where D is a Euclidean metric on n space. So this pair R and D is a metric space with Euclidean metric D. Secondly, our next proof is regarding Rn once again, but we shall prove that Rn is a metric space with a metric other than Euclidean metric. So what kind of metric we define here? It is quite different from the previous metric, and we define a map D of xy, sorry, D from Rn cross Rn to R by, how can we define D of xy is equal to summation I from 1 to n, here is a finite sum, mod of xi minus yi whole power p and whole power 1 by p. Okay, where p is greater than or equal to 1. Yes, p is greater than or equal to 1, so we shall prove that D satisfies the 4 properties of metric. Okay, so D of xy equals summation I from 1 to n mod of xi minus yi power p whole power 1 by p. So first of all, the non-negativity, since the function D involves mod here, and the mod power p where p is greater than or equal to 1, it is also non-negative, and then the summation of all these modulus power p is non-negative. This term is also non-negative. So when we take the power 1 by p, the pth root of this value, what we get, we will also get a non-negative real number. Okay, so a number which is greater than or equal to 0. So it can be seen that D of xy greater than or equal to 0. So this is the property of non-negativity, and in the same way as we have done previously, we can prove that, means it is not absolutely same, but the method is quite similar. You can also follow the method as before. For power 2, here is power p where p is greater than or equal to 1. So we can show that D of xy equals 0 if and only if x equals y. For example, if I would give you some hints, and then you will, I hope you can do it easily. So if D of xy equals 0, it means that summation I from 1 to n mod of xi minus yi or p whole power 1 by p equals 0. So this is possible when, because we have this number equals 0. And how it possible? It is possible because since we have this one equals 0, so when we take power p on both sides, what we have this value equals p, this one. Okay, and it is possible when each modulus implies that for each I mod of xi minus yi power p equals 0. Okay, and what is that? This implies that mod of xi minus yi equals 0, and uh, this is what we get here, xi minus yi equals 0, and for each I we have, this implies that for each I xi equals yi, hence we have the n tuple x is equal to n tuple y. Okay, so by following this you can go in the reverse direction to prove that when x equals y, then dxy equals 0. So this is done. Now number 3, the symmetricity of d. It can be done very easily, and you can prove that d of xy equals d of yx as before, because before in the previous case we have whole summation of whole squares. Here we have the summation of modulus, so we can change the direction of xi minus yi in that is we can write yi minus xi, and hence we have d of xy equals d of yx. So this implies that d holds the property of symmetricity. Then the next is that we shall prove that the triangle inequality holds. So we must prove that d satisfies the triangle inequality. So again, if z is equal to z1, no, here you must write that x and y. What is x and y? X is equal to x1, x2 up to so on xn, and here this is the n tuple, and then y is equal to y1, y2 and so on yn. This is the n tuple. So if z is equal to the n tuple z1, z2 up to zn, okay, then we shall prove that, then we show that d of xy less than or equal to d of xz plus d of zy. What is dxy? What is dxy? Or dxy is summation I from 1 to n mod of xi minus yi power p whole power 1 by p. Okay, this is our dxy. Very simple. Now we add and subtract zi in the modulus. Xi minus zi plus zi minus yi whole power p, the mod of whole power, and raised to the power 1 by p. So we just added and subtracted zi. You can see, take for each I, ai equals xi minus zi, and bi equals zi minus yi for each I. Okay, now what we do here, we shall prove that d of xy is less than or equal to d of xz plus d of zy. Now we see what will happen. Here this implies that d of x y equals to, here we shall put ai and here bi. Okay, I from 1 to n mod of ai plus bi power p whole power 1 by p. So what is p? P is greater than or equal to 1. When p is greater than, when p is equals to 1, the first case when p is equal to 1, what we have, we have summation I from 1 to n mod of ai plus bi. Okay, and this is obviously less than or equal to summation I from 1 to n mod of ai plus summation I from 1 to n mod of bi. Why? Because for each I we have a1, for each I equals 1 we have a1 plus b1 mod, which is less than or equal to a1 mod plus b1 mod. Then we have for I equals n an plus bn mod, which is less than or equal to mod of an plus mod of bn. So when we sum all the left hand sides and right hand sides of these n number of inequalities, this one, this one, this one, this one, so what we get, we get the answer in this way. Okay, so for p equals 1, for p equals 1, the inequality satisfies. Now for p is, what is the result for p greater than 1? What we have, here for p greater than 1, we shall prove that dxy is less than or equal to dxz plus dzy. So this is less than or equal to summation I from 1 to n mod of ai power p whole power 1 by p plus summation I from 1 to n mod of bi power p whole power 1 by p. Why? Because using the Minkowski's inequality, this number is less than or equal to this one. So we have applied the Minkowski's inequality here by Minkowski's inequality. So by Minkowski's inequality, this number is less than or equal to this one for p greater than 1. Okay. So what is AI? What is AI? This implies that dxy is less than or equal to, what is AI? AI is xi minus zi. So here I from 1 to n mod of xi minus zi power p whole power 1 by p plus summation I from 1 to n. What is vi? Zi minus yi power p whole power 1 by p, and this is equal to dxz by definition of d. If we see the definition of d, this one, so we follow this definition, so which is equal to dxz plus dzy. So the triangle inequality holds for p greater than 1, and for p equals 1, for p equals 1, I have shown that before, that I from 1 to n mod of ai plus bi is less than or equal to summation I from 1 to n mod of ai plus summation I from 1 to n mod of bi. So in this case and this case, the triangle inequality holds. Henceforth p greater or equal to 1, the triangle inequality holds. What does it mean? It means that this implies that D is metric on Rn. Hence, therefore Rn D, this pair is a metric space. A metric space with the metric D. What is D? D is defined above here, and this metric is not Euclidean metric. This is another metric. So we have proved that Rn is a metric space uh, by taking two different metrics, by defining two different metrics. The first one, in the previous case, we defined the Euclidean metric on Rn, and then we defined this metric in this case. So hence we have shown that, we conclude that Rn is a metric space, sorry, R and D is a metric space